Welcome to your lecture for Chapter 19. Now, you've all been anxiously awaiting this particular video, and I am sorry, but it takes a little time to make these, and I have 3 classes to do them for, so I'm doing my best to get them out to you as quickly as I can, and in a timely fashion. So let's just get right into things, shall we? So Chapter 19 is all about chemical thermodynamics, right? And we've already talked about thermodynamics in Gen Chem 1 when we were doing all the stuff with calorimetry and talking about entropy and enthalpy and heat and all that good stuff. So now we're getting a little bit deeper into things, talking about chemical thermodynamics in particular. So one of the things that we're going to begin with is the concept of entropy. This guy right here. And entropy simply is the tendency for energy to spread or disperse. Okay? And basically what it is a measure of randomness or disorder. Okay? So one of the things that students like to latch onto is the idea that, you're following the theme and desire of the universe for an increase in entropy by letting your room be dirty. And to a certain degree that is true. But let's talk about how we're going to talk about measurements of entropy. And the first thing that we're gonna run into or use is the thing called the Boltzmann Equation. Okay, and the Boltzmann Equation looks like this. We've got S is the symbol for entropy. We have K, which chemists and scientists love K for everything. K is the Boltzmann Constant times the natural log of capital W, which is the number of microstates. And we talked about microstates a little bit in previous material, but we're going to get sort of a new perspective on it here in this chapter. So entropy is capital S. K is the Boltzmann constant. And W is the number of microstates. I'm not really going to use this equation to do heavy, hard calculations very much because calculating the number of microstates is a very complicated process. But the just so you know, the value for the Boltzmann constant looks like this: 1.30806 times 10 to the minus 23 meters squared, kilograms, seconds to the minus 2 per Kelvin. Okay. Guess what? This bit right here, that's joules. Okay? And what the Boltzmann constant does for us is it relates average kinetic energy to temperature. Okay? So average kinetic energy is in that part of my unit, and then temperature is right there. So the Boltzmann constant gives us a way to put those things together. All right, so entropy gives us a way to talk about whether or not processes, like chemical processes, whether or not they are spontaneous or not. Okay, and the important part about that is that the entropy change for the universe is equal to the entropy change for system plus the entropy change for the surroundings, right? And positive changes in the entropy of the universe are spontaneous processes. Okay? And this ties into the idea that the tendency of the universe is for an increase in entropy. Okay? So any process that increases the entropy of the universe is a spontaneous process. Okay? And what that means is that spontaneous processes simply do not need any help to go. They happen on their own. Processes increase the entropy of the universe. Okay? And spontaneous processes happen all on their own. Okay? So let's take a look, a little bit closer look at some information that we can get from the Boltzmann equation without having to do any real calculations with it. So delta S, right? So the Boltzmann equation, let's put that back up here. K times ln of W, right? And change in entropy, delta S, is same as it always is, S final minus S initial, right? So if I take that idea and sort of expand it with the Boltzmann equation, we get the change in entropy is K ln of the entropy, not the entropy, the microstates of the products minus K ln microstates of the reactants. Right? And so if I condense that a little bit, equals natural log of the products over the microstates of the reactants. Okay? So looking at that equation, if my numerator is larger than my denominator, so if my microstates of my products are greater than the microstates of the reactants, I end up with a positive delta S, right? If microstates, let's sort of write that out, of products are greater, right? And delta S positive means spontaneous. Okay, so if my microstates of my reactants are greater, looking at that relationship mathematically, then I will have a negative delta S, meaning not spontaneous. Okay, so remembering microstates, let's just remember what microstates are at all. Microstates are simply different ways of for something to be. So if you increase the different speeds of particles, if you increase the different ways that they can move, if you make it so they can vibrate more or spin or do anything like that, you're increasing the ways that they can be, and the ways that something can be are the microstates for that thing. So if I, in the process of a chemical reaction, increase the number of microstates, my products will have more ways to be. I will get a larger number in the numerator of the Boltzmann equation there, and I'll end up with a spontaneous delta S. Okay. So this is lots of fun, lots of interpretation of things. Okay. So when temperature is constant for a process, the term we use for that is isothermal. Iso meaning same, thermal meaning thermal. So when temperature is constant, we say that something is isothermal. And so for any isothermal process, chemical reaction, so to speak, delta S for the process is the energy for that process, we say Q reversible, divided by temperature, which is equal to the enthalpy of that process over temperature. Okay, so for example, delta S for fusion is equal to the delta H for fusion over the temperature of fusion. Okay? So I can calculate entropy very easily from enthalpy and temperature. Okay, so for any particular process, melting, fusion, evaporation, all those things, I can calculate the entropy of that process. Okay? So a sort of more general way to write it. So if I'm looking at entropy of, for example, phase transitions. Okay? I can say delta S of the transition is delta H of the transition over the temperature of that transition. So when I say transition, I'm talking about fusion or vaporization, those sorts of things, okay? So, for example, if I want to know what is the entropy of ice melting to liquid water, I have delta H of fusion equals 6.02 kilojoules per mole at 273 Kelvin. Right? So my enthalpy of the transition is 6.02 kilojoules per mole. My temperature of the transition is wherever that phase change happens, whatever the phase change is. So in this case, the transition from solid ice, solid water, to liquid water happens at 0 degrees Celsius or 273 K. So I can write delta S of fusion is equal to delta H of fusion over the temperature of the fusion, 6.02 kilojoules per mole divided by 273 Kelvin. The enthalpy is 2.02 times 10 to the minus 2 kilojoules per mole Kelvin. Okay. Now, let's think about how this relates to whether or not this is a spontaneous thing or what it is. So when I go from solid water to liquid water, solid water, all of my water molecules are stuck together, stuck in place, they can't move, they can't do much. And then I transition to liquid water where now they're able to slide past each other and move around. So my liquid water state has more microstates. Okay? And thinking about the Boltzmann equation, if I have more microstates in my products, I get a positive delta S. Positive delta S because we have more microstates in the products. okay? And positive delta S means that this process is spontaneous in these conditions, okay? And the conditions do matter, okay? So, and we'll talk about this in a minute, about how temperature can affect whether or not we end up with a positive or negative delta S, okay? So let's take a little pause and talk about the third law of thermodynamics, okay? So there's a concept called zero-point energy, okay? And zero-point energy is simply the lowest possible energy state all right? And the idea here is, and why do we care? Zero-point energy is the starting point for calculating absolute entropy. Okay? In order for us to determine what absolute entropy is, science needs a place to start, and that is the zero-point energy. Okay? Now the third law of thermodynamics is that the entropy of a pure perfect crystal, which is difficult to say, a pure perfect crystal is 0. Okay, at 0 degrees Kelvin, at absolute 0. Okay, that's not okay. That is 0 degrees Kelvin. Okay, so the idea is that a pure perfect crystal at 0 degrees Kelvin. So at 0 degrees Kelvin, almost all molecular motion ceases. Okay, everything is basically held still, not moving, not shifting, not vibrating, not doing anything. So there's no molecular motion going on to create microstates. And if my crystal is pure and perfect, there is 0 disorder in that crystal. So with no motion and no disorder, the enthalpy or entropy of that pure perfect crystal at 0 degrees Kelvin has to be 0. Okay? All right, so let's shift colors back to black and talk about the second law. Okay, second law, and we've sort of already been talking about this. The second law says that the entropy of the universe increases for any spontaneous process. Okay, so spontaneous, just to refresh, when we say something is spontaneous, means that the process occurs on its own without any outside help. Okay. So what we're going to do now is we're going to sort of talk a little bit about how temperature can affect whether or not a process is spontaneous. Right? So on temperature and conditions. Right? So, for example, water going to ice. Okay. So, freezing, right? So, at 0 degrees Celsius, that is a spontaneous process. At temperatures less than or equal to 0 degrees Celsius. Okay? So you take liquid water and you put it in conditions where the temperature's equal to or less than 0 degrees Celsius. That's going to happen on its own without any trouble. Water freezing will not be spontaneous at different conditions. So if I have temperatures greater than 0 degrees Celsius, water is not going to freeze on its own. Okay? So spontaneous processes do have to have some temperature and conditions dependence. Okay? All right? So there are several different ways that we can determine whether or not entropy is going to increase. Okay? So things that cause increases in entropy, reasons for entropy increase. Okay? So one thing that will cause an increase in entropy, and this is an easy one, gases forming, from liquids or solids. Okay? Thinking about that, reason for that, more microstates. Okay? Anything that causes more microstates to be in our products will cause an increase in entropy. Right? Same idea. Liquids forming from solids, solids. Same idea. Number of moles of gas increasing. Okay. So same idea for all three of these things. We get increases in entropy because all of these things cause more microstates. Okay. In terms of molecules, in particular, entropy increases from increases in translational motion, rotational motion, or vibrational motion. Okay? And again, it's all about more microstates. Okay? So if I can increase the ways that a molecule can move, i.e. going from one place to another, that's translational motion. Okay? If I increase the speed at which a molecule rotates about where it is, that's rotational motion. Or if I increase the vibrational levels, that's vibrational motion. All of those things cause an increase in microstates. Okay? So thinking about different materials, so solids, they can only see differences in vibrational motion at vibrational only. Okay, so I can take a solid and I can heat it up, which causes the molecules to vibrate faster. But the molecules are locked in place, so they can't rotate and they can't translate. Okay, liquids, we can do all motion, but it's limited. Okay, in liquids, now the molecules can slide past each other and go around each other. The molecules can rotate, the molecules can vibrate, but it's still somewhat restricted though because the molecules are still stuck together. Okay, gases have complete freedom. Okay, so total complete freedom of all motion. They can rotate, translate, vibrate, and they're not stuck together, so they're not restricted by that physical contact that is happening in liquids. Okay, so the moral of the story here is that solids have the least microstates and thereby the least amount of entropy, and gases have the most. Okay? And thereby the most entropy. Okay? All right, so our next topic is going to look familiar after we start doing it. But at first, it's going to sound like something new. But our next topic is standard molar entropy. Okay, and we say S with the little circle. Anytime you see that little circle, it means that something's standard. Okay, so standard entropy, standard enthalpy, all that sort of stuff. Okay, and what it is the absolute entropy of a substance in its standard form. Okay, so really nothing particularly interesting. But using standard molar entropies, I can now do entropy changes for reactions. Okay, and here we go. You're going to see something familiar, I think. So this is the sum, N for products, of the entropy for the products, minus the sum and reactants, entropy for the reactants. Okay, products minus reactants. Right? Just like you did with Hess's law and enthalpies. It's exactly the same way to do this, right? So you already know this process, right? And you'll get standard molar entropies from tables. Okay? These are your tabulated values. They're done. They're figured out experimentally. Somebody else has already figured this stuff out. So all you have to do is take the numbers out of the table and do the same thing you did before with Hess's law. Now, let's do a little example. All right, so if I have a particular reaction, let's say I have 2NO gas plus O2 gas, making nitrous oxide, which causes acid rain in the atmosphere. What is the standard molar entropy entropy at 298 Kelvin. Okay. So let's set up the equation. So delta S for the reaction is going to be products minus reactants. So 2 times the delta S for NO2 minus 2 times the delta S for NO plus the delta S for O2. Right, just like we did with Hess's law. And you'll have a table of entropies. So delta S naught for NO is 210.8 joules per Kelvin. For O2 is 205.1 joules per Kelvin. And for NO2, 240.1 joules per Kelvin. Right? So now I just have to plug in these numbers into my equation and crunch the numbers. So what we'll have is delta S of the reaction is 2 times 240 joules per K minus 2 times 210 plus 205. And come out to find that our entropy is negative 146.1 joules per Kelvin. Not spontaneous. Okay. Now let's take a look at it in a slightly different way. So we're going to come back up and look at our equation. So on the left side of the equation, I have a total of 3 moles of gas. On the right side of my equation, I have 2 moles of gas. Right? So reactants going to products I have fewer moles of gas in my products than I did in my reactants. To 2 moles of gas results in a negative S, right? And that comes from the Boltzmann equation way back at the beginning of this talk. W for products, W for reactants. Okay, so this is important. You should be able to look at a chemical equation and without doing any numerical calculations, be able to get a sense of whether or not it is a spontaneous process for the entropy. Okay, so simply looking at this reaction based on the number of moles of gas in the reactants and the products, I can tell that S is going to be negative. Okay, just by the chemical equation itself, nothing else. Okay. So, with standard molar entropies, we can also get an idea of how things can compare just by comparing chemical structure and things like molar mass. So standard molar entropies generally increase with increasing molar mass. Okay, so as molecules get larger, the entropy, standard molar entropy, will generally increase. Okay. B. Entropies are greater for gases than for liquids and solids. And that comes down to the microstates again, right? Gases always have more microstates, so therefore they will always have more entropy. And third, we see a generally increase with the number of atoms in the molecule. And that kind of goes back to the increase with increasing molar mass. If I have more atoms in my molecule, I'm going to have greater mass. Okay, so just for example, if I have CH4 versus C2H6 versus C3H8, my entropies are going to be 183 joules per mole K, 229 joules per mole Kelvin, or 270.3 joules per mole Kelvin. Okay, so just based on increasing complexity and molar mass, we can see a clear increase in the entropy for these molecules. All right, so I'm going to recommend that you hit pause or stop, because I'm actually going to stop this video at this point because I need a little bit of a break, and we are about halfway through the notes for this chapter. We'll come back with Gibbs free energy.